show some demonstration of a speech form.
Obama to female that way. Because it's a card, you just have to sort out the No, I'm gonna add that.
Oh, no.
Oh dear.
Try it in Internet Explorer.
You'll laugh, but sometimes it works.
Or Chrome.
Internet Explorer
Yeah.
within the
Or
Chrome.
Chrome. Yeah, one of the
Apparently, if you have under 90 hours, 329 is not required.
It's at the bottom of the dock of the.
Oh, here.
I don't report it. That's what I see. I think I might just like put off. Pretty much. Actually, class and so I don't want to have to take a class and then like have it not required and then like, oh, it's like
What is the search engine?
Google.
Just type it in there.
This is Internet Explorer. Okay, we're dealing with not with
I might just take a Gen X and like 213 and 214. At this point I was thinking 329 and just 214. And that way my schedule would be
if it ever loads.
329 or 385.
Update now.
Cancel.
And then 213.
No song?
There's vibe control.
There's a. I have a vibe control in the dock.
Thursday off.
Song.
Drop the bass, Professor Jim.
I thought I had found the last time I demo using this system.
You have. There's another vibe control in the dock.
Where's this? Where is it? Maybe you can come and show me that.
Come on, Alfie.
I saw like people doing David.
Lawrence.
We were about
IT.
Oh yeah.
The United States has conducted an operation that killed Osama bin Laden, the leader of Al-Qaeda.
Hear Obama in a female voice.
Tonight, I can report to the American people and to the world. The United States has conducted an operation that killed Osama bin Laden, the leader of Al-Qaeda.
They hear Obama in the target voice.
Tonight, I can report to the American people and to the world. The United States has conducted an operation that killed Osama bin Laden, the leader of Al-Qaeda.
Okay, so you can do a lot of fancy things with speech processing, so you don't believe anything that you hear now. You can listen to Sarah, Khalid, and Al Gore and the other people. But you can probably understand this plot now, having had a course in analog signal. Okay, you can go through this, and I won't go through the detail of it. But what is more interesting is probably what you can do in restoration of a bent thing. There was something on Caruso that I saw. I don't know where Caruso is. Oh, Caruso, okay. Caruso was a very old opera singer. He sang many years ago when the technology was very bad. You can see that the system used to record his voice.
Oh,
actually works better. Okay, that sounds better, right? So you can read up on what they do, and then actually they compare the voice of Pavarotti with Caruso, and found that he lost a lot of high frequency signal, and then they boosted his high frequency spectrum, as you can see from this plot over here, whereas the original recording was pretty bad in high frequency spectrum. So they used Pavarotti to inspire his voice. Okay, when you look at Pavarotti, his high frequency spectrum is still very good. So that was all due to technology. You can visit this page on your own to find out more about speech warping and signal processing by Matt Montag. Okay, I'll stop here. You'll find that you can actually understand some of the things we talk about on that page with your knowledge in PC 210. So, we were talking about Bible or Bible, and then it was a rather short lecture. Go here. They should go further away. They should go over there. Okay? So, so let's talk about Bible. Bible is bounded input, bounded output. And we have to show that absolute integrability of the impulse response. If this is absolutely integrable, then it implies Bible. Bible means bounded input, bounded output for all possible inputs. This is for all input. Okay, and if the output is bounded, then the system is called Bible stable. And it turns out that this is a sufficient and necessary condition. Okay, and the proof is given in the textbook as to why it is sufficient and what is necessary, but the book actually does not explain what sufficient condition actually means and what necessary condition actually means. So let me give you a 1-minute tutorial on what sufficient condition is. If a condition is sufficient, okay, implies an outcome R, okay, result. Okay, let's call this an outcome. And this is guaranteed. Okay, so if a condition is sufficient, and if you satisfy the sufficient condition, you guarantee the outcome of the thing that you're trying to do, like getting an A on this course. Okay, the sufficient condition would be that you have to hand in your homework, do well in your homework, you have to attend all the exams, do well in the exam, and then do well in the final exam. Those are the sufficient conditions. The necessary condition, on the other hand, does not guarantee that you get the outcome to be what you want, but it is necessary. So one way to say what a necessary condition is that the not of necessary condition will guarantee the failure of the outcome. Okay, there's one way to say that. That is, say for instance, the necessary condition for you to get the A in this course is to hand in all your homework. And if you fail to hand in all your homework, you're guaranteed not to get an A in this course. Okay? So this is another way to define what the necessary condition. This is sufficient. This is necessary. Okay? So the textbook kind of used this kind of logic in proving the sufficient and necessary condition, but the textbook did not explain that. So I just want to explain these two logics. Are there any questions on these two logics? Okay, if not, then let's move on. And there were a number of tests that you were asked to do to decide if something is sufficient or something is bistable. That was actually on example 10.11. You're given a whole series of impulse response. H1t is equal to e to the minus t ut. Is this bistable? Apparently it is, because it's an exponentially decaying function. If you sketch it, it will look something like this. And that is surely absolutely integrable. So it must be bistable. And of course, what happened is another example which looks something like this, 2ut minus 1. This is just 2 times the unit step function. And if you sketch this out, it looks something like this. And then this is 1, this is t. And this thing goes all the way to infinity. Is this bistable? Is this absolutely integrable? No. Okay? So this is yes, this is no. Okay? And then there are other ones like h4 of t is equal to 2 delta t. Okay? Is this bistable? It turns out that it's hard to prove this because this is a very nasty function. This is called a generalized function or distribution. So instead of showing that this condition is satisfied, then the textbook actually shows that if you have an input f of t convolving with the output h4 of t, you will always get 2 f of t. So this is the output. You can see that the output follows the input. So if the input is bounded, the output will be bounded. So this one is actually bistable. Okay? And then the tricky one would be this one over here, which is h7 of t is equal to delta prime of t. Is this bistable? And you can test this. You cannot use this absolute integrability thing because this is a very nasty function. If you take its magnitude, it becomes something very, very strange. So the best is actually test with an input. So you test with an input h7 of t convolving with f of t, which is delta prime of t convolving with f of t. Okay? So, what happens is that this actually is the same as using the derivative property of convolution, the same as this. Right? This is the same as that. This just means the derivative of that. Remember this derivative property of convolution? Do you remember? This is the same as that. You remember, right? So I hope all of you remember that. Okay, Titus also remembers. So this is equal to that. Okay? So, but when you convolve with a function like that, you just get this function out. So y of t is just equal to that. But what happens if f of t looks something like this? If f of t looks something like this, if I differentiate this, I will get 0, and then a delta function, and maybe something that looks like that. Okay, because when I differentiate this, I get a negative of that. I get negative exponential. So you can see that y of t is not bounded. So not bipolar stable. Because I have a bounded input, I get an unbounded output. Okay, yes?
For H of 4, what if f of t is unbounded?
If f of t is unbounded, but
Or to be a similar.
we're going to look for bipolar stability. We will put a bounded input. There's no reason to put an unbounded input. Okay, we put a bounded input and test it, our output is bounded always. And in that case, it is, right? It is always bounded as long as the input is bounded. But for this case over here, you can see that you can have some input that looks something like this with a step discontinuity that if you differentiate it, it gives you infinity there. And hence it's not bipolar stable. Okay? I think we are done with section 10.3, 10.1 and 10.2. Let's go to section 10.3. 10.3 talks about causality and LTIC systems. Okay. So what is the concept of causality? Causality means that before you do something, nothing can happen. For instance, if you were to swing your golf club and the golf ball, okay, after you swing your golf club and the golf ball flies away. But it's not possible that the golf ball flies away before you swing the golf club and the golf ball. Okay, that will be non-causal. Okay. So everything we experience in this world is causal. We have to do something before something happens. And when that is satisfied, we say that causality is satisfied. Okay. So all our systems that we deal with in real life is causal. Okay. And we have a linear time invariant system that's also causal. We call it linear time invariant causal system. Okay. This C here stands for causal. Okay? So one way to think about a causal system is that the impulse response has to be equal to 0 for t less than 0, because what is the impulse response after all? Okay, if you have a linear time invariant system, LTI, defined by h of t or h of omega, you put in a delta function t, out comes the impulse response. This is the definition of a linear time invariant system. Okay, in general, that system looks something like this, that if I have f of t in here, the output is y of t is equal to f of t convolving with h of t. Okay, that's what we have in general. And the impulse response in this is a special case where this f of t is converted into an impulse. And that if there's no output before there's any input that comes about, this thing always looks something like this. There's no input at all for t less than 0. Okay, we expect no output for t less than 0. So that we call that this system being causal. Okay, when the impulse response has the kind of property that nothing happens until the signal comes in. Okay. So then section 10.2 is a whole series of examples. Like if you have the fact that, like example 10.12, GT is equal to f of t minus 2. Okay, I suppose this is the output and this is the input. And you're asked if this system is causal. Okay, I can think of this as being f of t convolving with h of t. Now look for the h of t that would make them equal to each other. What do you think h of t should be? Yes? Very good. Okay, it should be f of t times delta t minus 2. Okay, and you can actually use the delay property of the convolution to figure that out. So h of t must be delta t minus 2. Okay, so you have a system, you have an LTI system, and then you have an input coming out here. And then the output h of t is delta t minus 2. So nothing happens for t less than 0, which is good. Okay, there cannot be anything that happens when t is less than 0. So this is a linear time invariant causal system. Okay. And then you have example 10.13, where you have g of t is rec of t. Okay, g of t is rec of t. Okay, g of t is rec of t, and then f of t is u of t. Okay, is this system causal? Okay, so you can say that g of t is equal to f of t convolving with h of t. Okay. And then you can find h of t quite easily. And if f of t is u of t, then the g dt would be the f dt convolving with h of t. Okay? Then what is the f dt? The f dt will be delta t convolving with h of t. Okay, but from this you can see that the g dt must be equal to delta t plus half minus delta t minus half, right? So the g dt is just equal to that because the rec function is defined to be something that looks something like this, rec of t. T equal to half, t equal to minus half. So when you differentiate this, you get that. Okay, now you compare this with that. What do you think the impulse response of this system is? Impulse response of this system should be delta t plus half minus delta t minus half, right? Because this thing convolve with anything gives itself, so this thing must be itself. Okay, so this is h of t. Can everybody follow that? I have g of t given to be that. I know that the input is a unit step function. I know that the output and the input are related through this impulse response. I do not know what the impulse response is. So I differentiate this to get the derivative of g. And since using the derivative rule of convolution, I just need to differentiate this. I get the impulse over here. So this convolving with this must be the same as this function, because I can also find the derivative of g with respect to t using a direct derivative, and from that I infer that h of t must be equal to that. So this system looks something like this. Now, that I have delta t coming in, okay, but out comes delta t plus half minus delta t minus half, and the output looks something like this. This is my impulse response. Okay, this is 0 time. This is input. This is delta t. It looks something like this. Is this system causal? Yes? What is that? The other one is negative, right? Yeah, you're correct. This is negative. Is this system causal? It has an output even before you have an input, right? This output comes about, and t equal to minus half. So it's not causal. Okay, not causal. And then you have example 1014. Example 1014. The impulse response equal to the direct delta function plus a unit step function. So again, if you plot the output h of t, it looks something like that. It's the delta function there, but where does this start to be non-zero? When t equals to minus 1, okay? So this is something that looks like that, t equal to minus 1. And then the input is something to be an impulse that goes like that. Apparently something comes about even before you have an input, so this is non-causal. Okay? And then you have example 10.15. Okay? Yt is equal to cosine of t plus 5 f of t. Is this system causal? The input is, this is output. This is input. Okay? This may not be a linear time invariant system at all, because it cannot be written as convolution of output input. Okay? But you can clearly, by eyeballing these things, this thing knowing that yt is only dependent on the present value of f of t. It doesn't depend on the future value of f of t. Okay, unlike this kind of thing is kind of weird. It depends on values. Or something happens before there was an input. So for this system, when there's an input, there's always an output. The output always depends on the input. So this system is causal. Okay, this system is causal. And then you have another example. Yt is f of t squared. Is this thing causal? Okay, is this thing causal? So it's not causal because when you set t to be -1, when you set t to be -1, it depends on f of t to be +1. Okay, but y of t -1 is equal to f of 1. So apparently this is not causal because the output at t equal to -1 depends on the future value of f of t. Okay, non-causal. Okay. So there are many other examples, and I think they are not that interesting, but maybe this one is interesting. H of t is equal to omega over pi sinc of omega t cosine of omega t. Okay, is this thing causal? Just want to make sure that I get everything correct. Is this thing causal? Okay, this is actually omega naught. If I were to sketch this impulse response, it will be this function multiplied by that function, and sinc of omega t will look something like this. This is sinc of omega t. Okay. And then cosine of omega naught t will look something like that. I didn't draw it very well, but you know what I mean. Okay, cosine of omega naught t. The impulse response is the product of this function with that function. And it looks rather complicated. I don't want to multiply them together, but what you notice is that h of t, maybe it's 1 over here, but maybe it's something like this over there. I don't know. Okay, something like that over there, when you multiply both of them together. But what is to be noted here is that h of t is non-zero at t equal to -infinity. When t tends to -infinity, this function is always non-zero. This function is always non-zero. So this part is always non-zero. Which means that if you think of this as a linear time invariant system, if you put in an impulse, out comes this pulse that looks something like this. It has a very long tail. Something came out of the system even before you send in something. Apparently this is non-causal. Okay. So I think the others are kind of trivial. I think you can read about them. Okay, so there are lots of systems that are non-causal, but then when they're non-causal in the time domain, then you cannot implement them. But signal processing is also used in the space domain, where you might have an input y of x is equal to an input f of x convolved with h of x. Say x can be a position of an image or something. Okay, like in image processing. So in that case, then it's okay to have this thing be non-causal in image processing because you're dealing with images. For instance, your input f of x might look something like this. It's definitely not causal. Your h of x might look something like this. And then you want to generate an output that is convolution of these two, and you can have non-causal signals. In this case, actually non-causal images. And then you can manipulate images using signal processing technique, and this one is actually something useful that you might want to create, like what you do in image processing. So non-causal systems are useful, very useful in image processing. Okay, but we have talked a lot about low-pass filter and band-pass filter, and actually, are those systems really causal? Let me ask you this. That we have talked so much about low-pass filter and band-pass filter. For instance, one of the things that is our favorite is that the transfer function for the frequency response looks something like this. Okay. If I were to ask you to find the time domain correspondence of this, do you think you have a causal impulse response if I just plot the frequency response to be like that? So if you have a rect function, let's assume that this is the simplest, that we only have a rect function. What is its time domain correspondence? The sinc function. So this sinc function will look something like this. And is this causal? So it's not causal. So a lot of the things we talk about in this course, like low-pass filtering, actually correspond to non-causal systems. Okay. So this is actually just an idealization to make your homework easy. Okay, because then when you do low-pass filter, you just have to multiply by 1 inside the window and 0 things out outside the window. So most real-world filters don't look like this. They look a lot more complicated.